In order to understand shape, structure, intermolecular forces, everything that comes after this, you really need to understand Lewis electron dot diagrams. So before we can get into compounds, you first have to understand the Lewis electron dot diagram for individual atoms. So we're going to look at from family 1 to 8A, running across the third period, from sodium to argon. How would you do the Lewis electron dot diagram for each element of the third row of the periodic table? If we start with sodium, we begin by writing the formula for sodium, Na, and we know that sodium from family 1 has 1 valence electron. So we give the sodium 1 dot. There are 4 places that I can put electrons: above, below, left, and right of the symbol for the electron. It really doesn't matter where the 1 electron goes. It can go in any one of the 4 locations. If we move to magnesium from family 2, magnesium has 2 valence electrons, and they can go anywhere as long as they don't go together. We can't make a pair until every location has at least 1 electron. Aluminum in family 3 will have 3 valence electrons. Again, 1, 2, 3, you can put them anywhere you wish as long as you don't make any pairs, because each location hasn't received an electron yet. That happens when we get to silicon, which is in family 4. Silicon has 4 valence electrons. I now have enough to put 1 in each of the 4 locations. After silicon, we have phosphorus. Phosphorus is in family 5. When I put the 5 valence electrons in, now I'm going to make my first pair. Every location has 1 electron. The 5th electron makes a pair. This pair is known as a lone pair because it doesn't participate in bonding. It remains alone. Sulfur from family 6 will have 6 valence electrons, and it has 2 lone pairs. These single electrons are called bonding electrons because we'll see that they're what's responsible for bonding later on. We have chlorine from family 7, 4, 5, 6, 7. And then argon from family 8. Now let's describe what we've just drawn here. Sodium would be described as having 1 bonding electron. Magnesium has 2 bonding electrons. Aluminum has 3 bonding electrons. Silicon has 4 bonding electrons. When we get to phosphorus, we see our first lone pair and 3 bonding electrons. Sulfur has 2 lone pairs and 2 bonding electrons. The chlorine has 3 lone pairs and 1 bonding electron. When we get to argon, argon has a full octet, a full set of 8, a filled valence. It has 4 lone pairs and no bonding electrons. That's why it doesn't bond. To write the formula for a compound, we first need to decide if we have an ionic or a covalent compound. Ionic compounds have Lewis diagrams that correspond to ionic bonding, and covalent compounds have Lewis diagrams that correspond to its own kind of bonding, covalent. So each one shows exactly what's happening. For an ionic compound, because ionic bonding involves the transfer of electrons and the formation of ions, that's exactly what the Lewis diagram will show. For covalent compounds, we have sharing of electrons, and again, that's exactly what the Lewis diagram shows. I recognize that this is an ionic compound. It starts with a metal. I see a metal and a nonmetal. This is a simple or binary ionic compound. It has the metal calcium as the cation, and the nonmetal chlorine has become a chloride anion. First, I start by writing a Lewis diagram for one for each kind of atom in the compound. Calcium from family 2 will form a 2 positive. Chlorine in family 7 forms a 1 negative. If I can write the formula by balancing the charges, that can help me to write the Lewis diagram as well. So I need to do one of each kind of atom in calcium chloride. A calcium from family 2 will have 2 valence electrons. A chlorine from family 7 will have 7. The Lewis diagram for calcium chloride, an ionic compound, will show the transfer of electrons, and the calcium has 2 electrons to lose. It forms a cation. It will show where the electrons go, that they go to chlorine to form chloride ions. So the calcium I put in square brackets. I show the valence empty, even though I know there's an inner filled valence. I'm just showing the valence level. So I'm emphasizing the fact that it has emptied out. And I put the charge outside of a square bracket. Where do these electrons go? They go to chlorines to make them chloride. So if I write one chlorine with its 7 valence electrons, I have one empty space right here where I can put that electron. Next, I put a square bracket around the chloride and show its charge. But this only accounts for one of the 2 electrons that the calcium loses. So I need a second chlorine, just like it suggests in the formula. There's my second chlorine. It receives a second electron from the calcium and also forms a 1 negative ion. Now, the exact arrangement doesn't matter here, but you must show every single ion that forms. You can't put a 2 subscript, for example, like you would in a formula. You have to show the 2 chloride ions separately. Here I need to recognize this as a covalent compound. I see 2 nonmetals. I see the use of prefixes. I know that this is part of the covalent naming system and that this is a covalent compound. If I can write the formula, that will help me too. But I start, as I did before, by writing the Lewis diagram, one for each atom in the compound. So there's a phosphorus. It's in family 5, so it has 5 valence electrons. I see that it has 1 lone pair, which is not involved in bonding, and 3 bonding electrons. The fluorine, like the chlorine from before, is in family 7. It has 7 valence electrons, so I see that it has 3 lone pairs and 1 bonding electron. Now the atom that I put in the center is going to be the atom with the most bonding electrons. Phosphorus is going to go to the center because it has 3 bonding electrons. It makes more bonds than the fluorine. It can make 3 bonds with its 3 bonding electrons. Fluorine may have more valence electrons at 7, but it only has 1 bonding electron. The others are in lone pairs. So with the phosphorus in the middle, I know that there are 3 fluorine. They can each share 1 electron, so the fluorines share 1 electron and have their 3 lone pairs. There are 3 fluorine that are going to do exactly the same thing. The bonding electron will share here, and then the 3 lone pairs occupy the other 3 positions. So one more time. the third fluorine with its bonding electron and its 3 lone pairs. And now we're finished. There's PF3. Now I have another pair of examples for you, aluminum oxide and ethanol. We'll start with aluminum oxide. I recognize a metal and a nonmetal. I recognize this as an ionic compound. So if I can think about their charges and write the formula, it will certainly help. Aluminum is in family 3A and makes a 3 positive. Oxide comes from oxygen family 6A and it's a 2 negative. I think about the least common multiple for 2 and 3 as 6, and I know that I'll need 2 of the aluminum 3 positives and 3 of the oxygen 2 negatives to make a balanced or neutral formula. Writing the Lewis diagram always begins the same. I need to write one of each kind of atom so that I know what I'm dealing with. Aluminum in family 3 has 3 valence electrons, and oxygen in family 6 will have 6 valence electrons. 2 bonding electrons and 2 lone pairs here, and 3 bonding electrons here. Because it's ionic bonding, I know it's going to involve transfer of electrons. So the aluminum will lose the valence electrons and we show it empty. And I need to show both aluminum. The oxygen needs to gain 2 valence electrons. So one oxygen, which has 6 valence electrons, will gain 2 more to form an oxide 2 negative. These aluminums together have lost 6 valence electrons. This oxygen only accepted 2. If I write another oxygen with its 2 lone pairs and 2 bonding electrons, this oxygen can receive 2 more. We've now accepted 4 of the 6 electrons that were lost by the aluminums. When I put in the third and final oxygen, it's able to accept the last 2 electrons. So you see that in the Lewis diagram, we're showing both of the 2 aluminums in the aluminum oxide and all 3 of the oxide ions. We have lost 6 electrons from the 2 aluminum, and we've gained 6 electrons from the 3 oxygen that become oxide. Net charge is 0 because we have 6 positive and 6 negative. When we switch over to the second example, ethanol, ethanol is a covalent compound. It has a trivial or memorized name. There are keys in the formula to help us understand how it's put together. But again, we'll begin with one Lewis diagram for each atom. Carbon from family 4 has 4 bonding electrons. Hydrogen from family 1 has 1 valence electron, and oxygen in family 6 will have 6 valence electrons. But we know this is covalent bonding, this is sharing, so we need to share the electrons, not transfer like we did a moment ago. The atom with the most bonding electrons is the carbon. It has 4 bonding electrons, so we'll put carbon at the center. With a bit of experience and practice, you'll learn that when you see compounds like this, the carbons usually join together and make a skeleton for everything else to join from. If I started to put things around the carbon too quickly, I would only have 4 bonding sites with the 4 bonding electrons. But because the 2 carbon link up, they've used 1 bonding electron each to do so, and now I have 6 places to add other things. There's a clue here in the formula that 5 of the hydrogen are similar. Each one has 1 bonding electron and makes 1 bond. So that's 3, 4, and 5. There's actually a 6th hydrogen, but there's a clue in the formula that tells me not to put it in right away on the carbon. There's an oxygen that has to come next, using a bonding electron and putting in the 2 lone pairs, and then when we finish up, we have another bonding electron. And that's the place where the last hydrogen joins. So what you have to remember is to draw one Lewis diagram for each kind of atom in the compound. Then you have to decide, is this compound ionic, and therefore I show transfer of electrons and the formation of ions, or is it covalent, and then I show sharing of electrons. So that's it. Go do some practice.